Alright, I am going to try to get this one done in one video. I doubt it will happen though. We became experts at stoichiometry in the first unit, so hopefully just applying one new kind of conversion factor won't be that big of a deal for us. That new conversion factor is simply going to be using molarity to convert liters to moles and vice versa. Other than that, all the stoic will be the same. So the first two labs we did with the alum and figuring out the metal carbonate unknown involve what's called gravimetric analysis, just using a balance to measure the mass of objects, and that's it. But in the molarity lab, we did what's called colorimetric analysis, using color intensity to determine the amount of substance. And then next up, we're going to do what's called volumetric analysis, using a titration to determine the amount of a substance. So you most likely have not used a burette before, but that's what this is. It's for it's another volumetric kind of device where it's meant for very precise measurements of volume. Oh, back it up. Colorimetric analysis is also called spectroscopy. You can do spectroscopy with visible light, with X-rays, with UV. Doesn't matter. It just so happens we used visible light for ours. Alright, so a titration is just when you take a solution of accurately known concentration. That's called your titrant. So you're given an acid that you know the molarity of. And then you gradually add it to another solution that you don't know the concentration of, called your analyte, until the reaction is complete between the two substances. So the titrant is the substance you know the concentration of, and the analyte is the substance that you don't know the concentration of. You need to know the identity of both chemicals, but as long as you know the concentration of one, you can do the math to figure out the concentration of the other. So the point at which you've added just enough of the analyte to go with your titrant, the point where it's called stoichiometrically equivalent. It's where they're both the limiting reactant. You've run out of both ingredients at the same time. That's called the equivalence point, the point at which a reaction is complete. Now, sometimes we use different ways to determine when the reaction is complete. One way is to use an indicator, a substance that changes color at or sometimes just very near the equivalence point. Other ways to determine the equivalence point are via pH, electrical conductivity. There's several ways to do it. So in this instance, they've used an indicator, and it starts out clear, but then you slowly add base to this unknown acid until it turns a very faint pink color. Okay, the indicator here, phenolphthalein, changes color from clear to pink once it starts to become basic. So that's why you don't want it like super duper hot pink. You want it just barely pink for at least 20 seconds. And that's when you've added just enough base to go with your acid. Okay, so here's a bigger picture of what that will look like when you've done it correctly. So here's another diagram of what's actually happening here. Here they have their OHs in the burette. They have some kind of base here. And then they have acid in here. They've thrown in some indicator that'll change color once there's enough base in there to go with the acid. Looks kind of neat while you're doing this because there'll be a flash of pink just for a moment, and then it'll disappear, and then all of a sudden you'll finally be at the equivalence point or the end point. The end point is where the indicator actually changes color, and hopefully that's really close to the actual equivalence point. There's different indicators to use for different titrations. Alright, so here they added base to acid, and so at the end they're just going to end up with salt water and some pink phenolphthalein floating around in the Erlenmeyer flask. Alright, now this is way too pink. The end point has, oops, I'm trying to move my face so you can see this. This is way too pink. The endpoint has been passed. You blew past it. And now the solution is very basic. It's no longer neutral. You want to stop it when you've added just enough base to go with your acid. And at that point, it's neutral, and it'll just be very slightly pink. So what do you do if this happens? Do you have to throw it all out and start over? No, not if you have two burettes. Okay, if you have your acid in one burette and your base in another, if you accidentally pass up your endpoint here by adding too much base, you can move your Erlenmeyer underneath the other burette and simply do what's called a back titration. Add a little bit of acid to clear it up, and then go back and add a little bit more base and try to actually stop at the endpoint this time. So there's some knacks to this. It's not exactly an easy thing to pull off. All right, now reading a pipette is also not exactly a walk in the park either. With the pipette, when they're full of solution, that's when it's actually up to the zero line. I know, up to the zero line doesn't make sense. But the whole point of a pipette is to measure how much has been expelled from it, how much you've released from it. So you originally fill it up to 0, and then as you slowly let out solution, the meniscus will go down, down, down even further. And so the numbers run the other way, so you kind of have to think about that when you go to read it here. So this, you know, if you just look here, you might call that 5.5, and you might think the numbers go up like they do in a graduated cylinder, but they run the other direction. 4 is here and 5 is there. So right now it's at 4.5. Now, in terms of sig figs, remember you can always go one more digit past the smallest division on the instrument. Well, here, every little line, the smallest division here is 1/10 of a milliliter. So that means you can eyeball it and guess, basically, estimate, one digit past that. So to me, it looks like the meniscus, the bottom of the meniscus is right on the line. So I would say 4.50. Here, it's kind of in between. It's between, let's see, 4.8 and 4.9. I would say like 4.87. I think it's a little bit closer to the 9 than it is the 8 line. And then I'm gonna move my face again. This would be 5.00. Okay, so 2 decimal places are possible from a burette, which is good because you get at least 3 sig figs. All right, so 4.48 or to 4.50 would be acceptable for this, because when we're estimating, we're not always going to agree. 4.86, 4.87 on this one. I gotta move my head again. And then 5.00 on that one. Okay, so that's it for the, I guess, science of the titration, the technique of doing acid-base titrations. Now it's time to talk about the math. I'll stop here for now and start up a second recording.